So in this exam style question, we're told that the figure below shows a negative ion, which is a charge of -4e, so that's -4 times the charge of an electron, and is free to move in a uniform electric field. When the ion is accelerated by the field through a distance of 57 millimeters, parallel to the field, lines, its kinetic energy increases by 5.0 times 10 to the minus 16 joules. So the first thing we just need to think about is what direction are we even moving in the first place, and really that's kind of in the first question, is state and explain the direction of the electrostatic force. The reason that's why that's going to be the same as the direction we're moving in this one is that we're just allowed to be accelerated by the field. The idea is they put in the electron and kind of let go. Sorry, not the electron, excuse me, the ion. To be clear, we're just dealing with an ion here because it's got actually 4 times the charge of an electron. The idea is we just put it in this field, we let it go, and what's going to happen? Well, which direction it's going to move, or which direction does it experience its force? And that's really the first thing they're asking. So like to state and explain the direction of the electrostatic force on the ion. How do we do that? What we've got to remember is, what do these field lines show? Well, they'd show us the force that the force that a positive charge experiences, the direction that a positive charge would experience a force in. So these field lines show us the force that a positive charge would experience, but this ion is clearly negative, so it's going to experience a force in the opposite direction, so its force is going to be this way. So it's clearly going to have been moving this way too, so it's moved 57 millimeters in that direction. That's what it means by parallel. So we're going to experience a force in the left direction. What we'll do is we'll just say opposite to the field lines, because that seems a bit more, scientific than saying left in this case. So what we're going to say is that it's going to experience a force in the opposite direction of the field lines. And why is that? Well, because there's a negative charge and field lines show us the direction of force a positive charge would experience. So let's write that down. So we see that it experiences a force in the opposite directions of the field lines as the ion is negatively charged. And that's what we need to say there, and that gets our 2 marks, one for saying the correct direction, one for saying the correct explanation. So then I'd like us to calculate the magnitude of the electrostatic force acting on the ion. How do we do that? Well, that's a bit more complicated, right? Because we know, really what do we know? We know the charge on it, we know that's our Q, and we know that the distance it's moved, and we know its kinetic energy increase, but that's it. How do we work out the forces experiencing in that? Well, there's 2 things we need to do. The first one is just to remember something. Remember, this is a uniform field, and so as we were saying previously, a uniform field means that the force experienced is constant. There's a constant force in a uniform field. Just as we have for gravity, the field strength is actually constant everywhere, and so too is the force experienced by a particle in this uniform field. So that tells us that its force is constant. So what can we do then? Well, we know its change in energy, and we know its distance it's moved through, and we know we've got a constant force, so let's use the formula for work done. So the field is uniform, so our force F is constant, which means we can just use our work done formula, that the change in the work done is just the force times the distance you've moved in. Now we can do this quite simply, because we know that the work done is just your change in kinetic energy, so it's your change in EK. That's just going to be equal.
Hey guys! To continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the Snap Revise smiley face. Join me today, and together let's make A-level physics a walk in the park.